Okay, so in this video, I'd like to talk about the penalty method of handling constraints. Okay, so basically what the penalty method does is it adds stiffness to our system of nodal equilibrium equations, all right, without altering element properties like like setting A or I artificially high in order to enforce constraints. Okay, that's the brute force way to do it. The penalty method is, I guess, one shade lighter than the brute force approach, okay, of changing element properties. All right. So the basic idea behind the penalty method is that we use quantities that we know how to form, like KFF, PF. This contains all the load effects, so that's PF tilde, let's say. All right, as well as CF and R. Okay, CF shows up on the left and the right hand side. But basically, what we're doing is we're taking this matrix triple product, CF transpose alpha times CF, and treating those as basically artificial springs that are added into our system of equilibrium equations. Okay, and we add that into the added in basically in parallel to the stiffness of the unconstrained structure. Okay, so CF is the constraint matrix. Okay, alpha is a matrix that's diagonal with every entry alpha II equal to the so-called penalty number assigned to the ith constraint equation. Okay, usually the penalty numbers are the same for all the constraints. All right, so alpha just reduces to a scalar times the identity matrix. Okay, but as alpha gets higher and higher, we're adding more and more stiffness into our system of equations. Okay, and we're also adding in some force on the right hand side to compensate. All right, through CF transpose alpha R. Okay, so as equation 1 is solved with a sufficiently high value for alpha, then the constraints become enforced. All right, so we're just adding in artificial stiffness and force on the left and right hand sides of our system. Okay, so in terms of the stiffness matrix, one of the key things is that the penalty method does not alter the size of KFF, all right, but it can lead to a different topology. It could increase the bandwidth compared to the original KFF when we drop in this term CF transpose alpha CF. All right, it can change the topology of our left-hand side matrix. Okay, so that can increase the computational time for solving the equations for large structural models. Okay. Also, in terms of recovering reactions, kind of like with the Lagrange method, with the penalty method, we can obtain forces or so-called penalty forces that correspond to fixed end basic forces for each of our constrained elements. All right. So in terms of the the Lagrange multipliers, okay, we can compute something like Lagrange multipliers from the penalty method by multiplying alpha times CF UF minus R, right, which is just our constraint equations. Okay, CF UF equals R. Okay, so just move that over to the left-hand side. Okay, and then as the constraints are satisfied, right, this equation here becomes closer and closer to 0. Okay, and then from that we can get these basically penalty forces that we need to add into the elements during force recovery. Okay, so just like with Lagrange multipliers, right, we add in this PB lambda, where each lambda comes from a constraint equation. All right, so for an axially rigid element, we'd have, say, lambda 1, which is the force that would impose UB1 equals 0. And then for a flexurally rigid element, we have lambda 2, lambda 3, all right, which impose UB2 equals UB3 equals 0. Okay, so that's what goes into, or what comes out of PB lambda. Okay, so in terms of the implementation, all right, to solve equation 1, we need to specify an equation, penalty number, alpha, just say like 10 to the 8th, and we'll look at what that penalty number should be in later examples, all right? And then just form KFF and PF for the penalty method by just adding on the penalty terms, okay? Alpha times CF transpose times CF, okay? And then alpha times CF transpose times R, and then solve for the nodal displacements, all right? Then we can recover the penalty forces with this expression for lambda, okay? And then use those to recover reactions, okay? So I just wanted to give a quick overview of the penalty method and some of the implementation features at the structural level, and then we'll look at an example to see how this works at the element level, okay? Thank you.